I wanted to spend a moment talking about the Minecraft world format because there are not a lot of resources, with the exception of existing code bases that read and write world files. So my intent here is just to take some of the information that I've gathered and synthesized in the process of writing my own mapping tool. There are things that I have struggled with as far as like data not quite coming out in the way that I'd expect, and other just idiosyncrasies with the format and dealing with it. I am going to talk exclusively about doing this in a PHP context, but the principles are the same regardless of what language you're using. We can get more into the specifics here in a moment, but I basically wanted to talk about the newer Anvil world format, which was introduced in 1.2.1. Anvil is going to be the sort of overarching file format. Like the files that are actually written to disk are in this sort of schema. That replaces the region format, and primarily the way you tell those apart, if you're looking at just the files from a Minecraft world, is whether the world files end in .mca for Anvil or .mcr for region. So right now I've got all of these files indexed by their relative location of the world origin, and they're all .mca. Within each region, there are a certain number of chunks. 30, I think it's 32 chunks by 32 chunks. I'm already, it's been sort of months of research in the off hours, so some of the details are actually a little scant. Okay, sorry, I should have had this prepared. The region format is still where a lot of the information about the specifics of how data is organized is stored. Anvil is just has a bit, but like this is only explaining the differences between the new and old format. So the vast majority of it still agrees with the region file format. So there's 32 chunks per side within a region. That even references going back farther for a different format. So the primary benefit of Anvil over region is that it just takes up less space. It's more optimized, and they've done that in two ways. One of which is dividing chunks into, I think, what are called sections. So vertically, they're actually chopping each chunk into sections, and you can like sort of seek in the file to both into the location of a chunk or to the location of a section within a chunk. If a chunk has been generated, it's present in the file. If it hasn't been generated, it'll just be a zero length sort of block, if you will. Other things that I was interested in while learning about this, for my purposes, which I guess we should sort of look at here. My goal was to create a map rendering tool that can effectively render height map data, or maybe a little bit of additional information in the way of like, well, water, land, perhaps grass, sand, like a few identifiable things for specifically like readability of the map. And I paused at a point where I was happy with the output, and kind of wanted to reflect on what I had done to get to this point. So right now you can kind of see these, like the stippling here with some not natural looking things. This happens to be where I was occupying this world. I'd planted a bunch of trees on this sort of central area of this island. The origin is somewhere around in here. But you'll notice that somebody else is in here, having planted a grid of trees. I think we saw a moment ago a larger structure up here. Yeah, there we go. So it's doing a pretty good job of rendering like identifiable characteristics of the terrain, and even has a little bit of detail under the water here. Okay, so to get to that point, I needed a way of moving from individual, mapping in an individual map tile. So I'm just going to open one of these in a new tab here, or individual locations on the map, which we can dig in here. We can get into the specifics of this rendering here, but Leaflet is the JavaScript framework, and it basically translates this infinite canvas here with a zooming feature into tiles. That tile format is, if I can remember where all my stuff is, defined when you initialize the framework in the client or the browser. So here it's just pointing to a route that we have in our PHP application that accepts a zoom level and then an X and Y coordinate. The X and Y coordinates here are actually have no direct relationship to the resource or the world files, because Leaflet doesn't know how Minecraft coordinates work or anything like that. So if we're loading, say, tiles zoom level 4, x2 and -2y, that actually doesn't correspond to, say, a specific region file, except in a sort of funny case where you're zoomed all the way out, and then it does coarsely relate. But I've worked on some functions that translate between Leaflet coordinates in this space and Minecraft world coordinates. So at this maximum zoom level 4, each map tile actually ends up, don't want to block that, inspect. Each one of these map tiles actually ends up being, I believe, whatever, 16 by 16, is that correct? One chunk? No, it's more than that. Or maybe we were zoomed out. We did 5. Okay, at zoom level 5, then we get 256 individual rectangles that are rendered out into this SVG graph. This is not very identifiable because of the lack of variation in the terrain, but there should be, oh no, there's still more than that. So maybe this is more chunks than I'm thinking of. In any case, the app is able to render out those SVGs strictly based on the path or route in the app. Okay, so going back to the file format, the basic principle with this is that every block in the world obviously is stored in a region file. And it's fairly easy to figure out based on a block coordinate in game what region file that block is in. It becomes a little bit more difficult then to seek around in the file and actually get the data about that specific block. Generally speaking, when you're in a multiplayer world or even a single player world, you have a server and client sort of relationship, and the server just sends all the chunk information to the client. You don't need to like figure out exactly what block, like all the block information is sent to the client, and then the client can, you know, render it beginning to end. But in our case, we actually just want to chop it up and select certain portions of it. It's still almost always done chunk by chunk, though. And the reason for that is because the chunks are, actually, let's go in here. The chunks okay. The chunks begin with 4 bytes that describe the length and then the type of compression that each chunk uses. To locate a chunk, you actually have to refer to a table in the header. And we'll go through the math here, but basically there's an index at the beginning of the file that describes, at the beginning of each region file, that describes where each chunk is stored in the file. And that may move around, so you can't just automatically assume that, you know, because we're in the, if it's 32 chunks by 32 chunks, we can't just assume that chunk 32 in the, let's say, the upper right-hand corner of a region is 32 times, you know, the amount of storage that each chunk takes up. Because not all the chunks have been generated, there's other reasons that chunks sort of like vary in size, including like the last section, vertical section within a chunk that is occupied by a block. It's just able to compress the rest of it, saying it's just air, and forget about it. So that chunk will actually take up less space on disk and in the region file. So this header table tells you where each chunk exists, or what the like data location of it is within that file. So the first task you have to do is looking up. Okay, so you've determined which region file your block or chunk is in, based on, you know, some incoming data like the X and Y coordinate from each tile in the map. You have to go look up where that chunk is going to be in the header. That will give you a location. The location, though, I believe it is not just bytes. It's actually a number of a 3-byte integer that represents the number of 4 kilobyte sectors that you have to skip before starting to read that. Read the chunk data itself. Also worth noting, the headers themselves each occupy 8 kilobytes, or 2 sectors in this 4 kilobyte sort of grid, if you want to call it that. I don't want to call it chunk because we're using chunks for an actual description of a game object or concept. So the header table, though, is always going to occupy 2 sections or 2 sectors of 4 kilobytes. So to look up the location of a chunk, you can refer to a reliable location within the header. If you get to if you seek within the header to a specific chunk index, which they've given a formula for here, and which I've implemented. We can look at the code. You will always, the data will always be in a reliable place. So you can use that formula, seek directly to those bytes, lift those bytes out of the file, and it will be in this format. You don't have to worry about whether the chunk has been generated or anything like that. If a chunk isn't present in the region file because it hasn't been generated or migrated yet, both fields are 0. So it would be no offset, no sector count. There's no chunk data. Done. The other cool thing about the table, the first table tells you where the offset is for the chunk's data, and then the second actually tells you when it was last updated. So you don't even have to seek to the chunk data to figure out whether it's been updated. And this is going to be really important in a moment because it allows us to do some really smart caching and refreshing. So, for example, you could take, for what is a fairly large multiplayer world, unbounded, there's been lots of exploration done, multiple gigabytes of region files. You can just scan this folder for region files that have a modified date, a recent modified date, without even opening them. And then look through that second table of timestamps and then update just the chunks that have had modifications to them, or chunks that whose updated time don't match some cached updated time that you have in your application. Right now, this is all, every single request to the tile is generating it. It's seeking to the point in that file. Or there might be some very minimal caching built in. So this is like completely unoptimized. If you were to take a individual tile, go make a modification to it in game, and then refresh that specific tile's URL, it would be instantaneous. Doesn't actually propagate to the browser, but step by step, I guess. Okay. So we've gone through the header, and now we know how to look up where our chunk is. 3-byte integers are not really like a common format, so you have to do a little bit of work to make this like a traditional, in this case, it'd be like 32-bit integer. And not many platforms support like arbitrary, in this case, like 24-bit integer. So you could, in this case, you just have to like create a byte, a multi-byte expression, and then, or like a hexadecimal value on your own with an extra 0 at the beginning for that most significant bit that is not present here. All the chunk offsets will fit within this, but fit within the 3-byte integer or 24-bit integer. Right, we talked about timestamps. Epoch seconds is just like a Unix timestamp, so this is pretty easy, and that is just a 32-bit integer. There is some discussion in some of these values of endianness, and that basically is a description of whether the most significant bit is first or the least significant bit comes first. So, and that might be front to back, like byte 1, 2, or sorry, byte 0, 1, 2, 3. But then the bits within that byte also may have endianness. So there are special ways of handling multi-byte. It's when like the first bit of this actually comes just before the first bit of this, or sorry, the last bit of this. So it's kind of like a little loop, if you can call it that. If my lack of computer science background is shining through here, then hopefully that's a bit encouraging, that like this is opaque but not impossible to reason through. Okay, so now that we know where a chunk is in the region file, we're responsible for unpacking the data. At the very beginning, as you seek to that point in the file, so from this offset here that we've gotten, the 24-bit offset integer, we seek that number of sectors. So some 24-bit integer times 4,000 bytes, or 4,096, I think, because it's not just not 4,000 bytes. It's powers of 2. There's your 4,096, right? Okay, so the very first piece of information you have is a 32-bit big endian, or 4-byte signed length field, basically an integer, 4-byte integer, 32-bit integer, that describes the length, again in 4 kilobyte sectors. The 5th byte represents a compression type, so that'll have an integer in it, 1, 2, or 3. As far as I know, the only compression type I've observed in any of the files I've looked at is number 2, or z-lib. And then 5 through the end of the length. Oh, I'm sorry, this length is directly in bytes, but the total length of the compressed data will almost always be in multiples of 4,096, because I guess it just makes more sense to be able to seek it in these sort of 4K chunks, or sorry, not chunks, 4K sectors, because what would they do with the, like, what is the remaining data there, if the next thing has to start at a multiple of 496 anyway, 4,096. Right, so we've been able to get all the way to this point, but here's where the major performance hit comes in. Each chunk is compressed, and there is some overhead when going and reading each of these tiles, or all the chunks that exist in a tile. It is a non-zero computational cost to decompress that every single time. We don't have to recompress it, though, because we're not writing anything to it. So again, this is an expensive step. The other expensive step is that specifically in this implementation, I'm using a package called NBT, Aternos, NBT, which is an NBT syntax parser written in PHP. That instantiates a ton of classes and has a bunch of cyclical references and all sorts of stuff that make the memory footprint of it significantly larger than it needs to be. There might be a leaner version of this, or even a way to do it without a library at all that just doesn't need to instantiate classes for each of the values, and preferring native PHP types instead. Fortunately, there are some like lazily evaluated and instantiated objects, it seems. So if you don't need access to a certain thing, it won't actually parse a value or try to unpack something. You haven't made some indication that you need it. Okay. So once you've taken bytes 5, or sorry, I guess that'd be byte 6 through the end, and decompressed it, then we get into another data format. Everything inside of the compressed data, though, is in NBT format. Named binary tag. It's basically like a serialized data structure. It's like not quite JSON, not quite PHP serialization. It's just, I don't even know who manages the spec for this, but you can't just grab a piece of data out of here. It has to be fully deserialized and unpacked into these data types. So like I said, there's in the Aeternos package, there are classes that represent all of these and special APIs for interacting with those values. This is mostly self-explanatory, and once I was to this point, things basically worked the way I expected them to. So we'll come back to this. What I'd like to talk about, though, is just what this looks like in an implementation. Again, it's been a moment since I actually did most of this development work, so I'm a little rusty, but there's a few things I want to look at. These two files, and then I want to look at the region file. Okay. So the first thing we talked about was how leaflet is using this like unbounded plane and translating it into coordinates. One of the core things here is the title to region function. And this is basically a way of taking the zoom x and y in, it's important, x and y in leaflet space, and instantiating a new region class with the formula that takes those coordinates and maps them into the x and y, or in Minecraft terms, x and z, actually, or what these are. Y is the vertical, or like altitude in the game world. So you have x, which is your east-west axis, z, which is your north-south axis, and then y, which is your elevation. But y, of course, is not represented in these because this is the region files are only concerned with like the horizontal and vertical position, with, well, not vertical, but like from our eyes, the east, west, and north, south directions. And then the world bottom to world height is all stored within a single chunk in there. So it's there's a moment where we're going to flip from using x and y in like tile related functionality to x and z, which is like Minecraft world coordinates. Okay, so this is the very first thing actually that the controller does at the top of this render tile. It comes in with the zoom level, the x coordinate, and actually what I end up calling the z coordinate here, just because that makes sense. Like we're never, the only time that we refer to this as y is in the front end. I'm trying to think here, routes. There we go. Web. So there's our x and z. These I think are important actually, because they map specifically to named arguments in the controller action or control method. Okay, so first thing we do is try to look up a region based on the zoom x and y coordinate. If we were to try and access something like API tiles, zoom level 0, 100, 100, we would get back an error there because that region file just doesn't exist. And there's a special template that renders out an SVG with that information in it. So if you seek way out there in the map, it'll start to produce just these error tiles. Okay, we then go on to see in that coordinates file, I believe, tiles per region. This is how many map, like leaflet map tiles fit in a given region. And that basically just takes a zoom level and translates it, and raises 2 to the power of that zoom level. So 2 to the power of 0 at this means that one tile there is one region per tile, so every tile only has to open up one region file at most. And there's never tiles that render across multiple regions. I just chose to do that because at that point, I believe these graphics are 256 by 256, so we end up with 16 times 32. Right, so on a like pixel double screen, you would have an SVG that generates effectively each physical device pixel corresponding to a Minecraft block in the world. Leaflet allows you to customize the dimensions of your incoming map tiles, or to render tiles that are like you can specify that there is a high and low resolution versions. But since we're using SVG, you can just render them in the SVG coordinate space there. We'll get into the rendering here in a minute. Okay. So we know how many chunks there are horizontally and vertically. So the edge here is like how many chunks are there going to be in the tile that we're rendering. Similarly, oh wait, we already got tiles per region, right? Okay, so the next thing we need to know is where we are within the region. So something that's super useful throughout this process is taking positive modulos. The offset of a chunk in world coordinates is in the first table, being the header table, can be found by using formula 4 times x coordinate mod 32 plus the z coordinate mod 32 times 32. That would be z mod 32 times 32. Unfortunately, when you do modulo operations on negative numbers, the behavior is a little bit erratic between systems. So mod positive is basically a way of just taking the modulo twice, and it is safe to do with a negative number, and it's safe to do with a positive number because for positive numbers, your number modulo n plus the modulo, or rather if you, no matter how many times you do this operation, you will end up with the same number. So it's safe to, I think you'd call it like idempotent. Basically, you can invoke the same thing repeatedly on a value, and it will always resolve to the same final value, negative or positive. However, just doing number mod or x mod n is not guaranteed to give you a consistent result, nor is just straight taking num mod and mod n. You have to sort of wrap around. So this takes, that this will be, this value will be at least within the modulo of 0, negative or positive. You can add modulo to it either to bring it above 0 and then take the modulo of it, or it will extend beyond the positive modulo value and you just mod back down to the sort of constrained one. I'm sure there are better explanations of that, but this comes in handy in a number of places throughout the format. Okay, so right, I just have a class here that helps with like multiplying and managing coordinates. Vector is not a great word for this, but it stores xy, xzy coordinate information. And they're putting in the x and z. In this case, this vector represents the number of, I believe, chunks that the offset is, because we're multiplying by the edge there. So with that offset, we are using a function of the region class that we instantiated back here in our tile to region, which returns a region instance. Look at that, get chunks from. Accepts the offset basically from that we determined in the last one, and then how many chunks horizontally and vertically we want. These are alls, width and height are always going to be the same. So from the controller, we basically just want a tile's worth of chunks there. So if there were 32 chunks in the file we're looking at here, I don't know if I want to start rendering a real one, because that actually ends up taking up a lot of compute power at zoom level 0 at least. So right, we're getting a list of chunks. This just returns, I should have mentioned, the backend application here is written in, or is done in Laravel, using very few Laravel features, Laravel specific features, except this resources directory for storing arbitrary stuff, and this collections class, which has been extremely useful. So at this point, we're basically just doing 2 nested loops. We go and grab or push into that collection a number of chunks. The position of a chunk within the file, the file doesn't actually have a notion of like x coordinates and y coordinates. It's literally just a list of chunks, and they go from left to right, top to bottom. So you go through the first like row, so x0 through, sorry, x0, y, no, x0, z0 through x16, z0, and then you go on to x0, z1. So in this case, we're looping across that first row, and then, well, I guess in this case we're actually going x and then down. So it's actually kind of like columns. It doesn't really matter. The order of these is not super important. However, I believe that something changed between in the region and Anvil format that makes compression a little bit easier. I can't remember if it's at the chunk level or the block level. Okay, so up to this point, we still haven't actually loaded any data. All we're doing here is getting classes set up for ourselves to then work with later. So once we know what kinds of data or where the data is that we want to access, then we can start going and fetching it. So these chunks may not exist. Again, we're just instantiating a chunk class here. So open up that file. The constructor of the chunk class, which represents just an individual 16 by 16 block chunk, so this is the minimal caching that we're doing here. As it's instantiated, it will just go and grab the data, decompressed data out of the cache if it's there. Otherwise, it just sort of silently passes down through. It also clears the cache if it believes that the last modified date from that timestamp table at the header of the region file is more recent than what we have in the cache. So that would be modified date, getting that out of the cache, So if we did have something in the cache with a last known modified date and our date is greater than whatever was in the file originally, so when it was cached is more recent than what the file is reporting it was modified at, then we just go grab that from the cache. If we had cached something and the date is earlier than when the file or when the region reports that chunk had been modified, then we just go and trash that cached information we had at that. But again, we haven't actually loaded the chunk data. This is still all just operating on the headers of the file, unless we have cache data, and then it will just load it right out of the cache. Okay, get chunks from, cool. So now we have a list of chunks. We can actually even filter that down to see which chunks have data. So chunk get data length. This is an example of where we're actually looking up in the region file a specific byte offset and then reading bytes out of it. So in that case, the raw data looks at the region file, its locations. So, well, the region file does get loaded, but we're not actually like doing any heavy lifting with it. So we just read the whatever 10, 15 megabyte region file into memory, and then seek to specific portions of it. So we have the header table, complete header table, and then we have the complete locations, chunk locations table, and the complete timestamps table. We know that the header is about 8K long, and we know that each of these sections is 4K long. The timestamps table is 4K long, but it's offset by 4K because the locations portion of the header comes before that. So this is two 4K sections here, and that's the full 8K header. The remainder of the file is, we're just taking the remainder of that. In PHP, the easiest way to look at this, or to read this stuff in memory, is actually just with a string. So we're basically buffering the entire file into a string, and then chopping it up into other segments. Again, in PHP, you can work with strings basically as data. A string is just a series of bytes, or in some cases like multi-byte characters, but fortunately all of this is within like a pretty standard like space, or we don't need any indication that they are multi-byte characters because it's just bytes. So for our purposes, strings are bytes, and you can slice them up. And when you slice them with an integer, you get bytes, or another string of. These don't print to the screen well. It's totally garbled, again, because it's just binary data, and it doesn't know what the significance of any of those individual characters are, again, because they're just bytes. It just happens to be pretty easy to work with. Okay, so the chunk is able to look up in its region's locations data a particular location and byte length. So in this case, we're just trying to get the length of the chunk data. Each one of the lookup cells is, or sorry, the chunk location information bundle, if you will, in the chunk location table or header is 4 bytes. So we're actually going to take 4 bytes out of there, seek to the location offset, which is, again, a specific format that corresponds to this formula. And this is our first use of that mod positive function as far as looking up data. So 4 times the mod positive of chunk, or the mod positive of the X location, by 32. Same with this, and then times 32 for the end there. This is, I wish I had a visual representation of what that looks like, but it's kind of a clever way of giving every XY combination a unique one-dimensional location within the header there. So this is the location offset here is just where this chunk is going to be within the location header. We know the length of the header. Where were we? Right. Because it's just a stat, like every one of these pieces of location information is 4 bytes. So all we need to know is where that begins. We're going to read 4 bytes out of it. We only need the first 3 though to get the offset. The second portion is the data length, so we're actually doing the same thing. This data, like that code is exactly the same as this. We're just getting that same location data out of the header, which is, again, a super fast operation because it's just slicing up memory. But instead of taking the first 3 bytes and padding it with a leading 0, and then unpacking it from the 3-byte integer in hexadecimal there, this is just a null byte character. This PHP unpack function is pretty inscrutable, but I guess pack is the spec is. So we're using n, unsigned and long, always 32-bit big endian byte order. So calling back to the order of those bytes. We're saying, hey, we have some data here, some bytes, and we want to say, hey, we treat that as a 32-byte integer. 24 bytes from the 3 bytes here, or sorry, 24-bit from the 3 bytes here, plus another 8 bytes for a total of 32 in our padded 32-bit big endian number. We're saying, hey, treat that as a 32-bit big endian number. The pattern, that part of the pattern is going to be named LOC for location, and then PHP hands that back to us as an array with keys. So if you had, technically if you had, we could do this in one operation. We could say like, hey, it's actually 3, we could make it into a 5-byte string with a leading 0 and say, hey, there's a 32-bit integer followed by a single byte integer, or an 8-bit number. I don't even know. Yeah, the most this can actually do is 16 bits, but the unpack function gives you the ability to basically pack and unpack data into bytes, and then reverse it out based on a sort of template. So all we're looking for is a 32-bit number from those 3 bytes with a leading 0. We get that offset, and then we multiply it by the chunk sector length, which is that 4 kilobyte. So that tells us where the data begins. Same deal down here. We're just taking the last byte of information from their 4th byte sector count and putting in 3 leading 0s, or 3 leading null bytes. So we're also able to unpack that as a 32-bit integer. This is probably wildly inefficient, and there is apt to be a better way to convert between some arbitrary string into an integer. I am not familiar with that. PHP's type juggling is not smart enough to know that we want an integer from the byte of a thing rather than an integer representation of a string, which in a lot of cases is just like 1, or if something looks like a number in like the way a human would think about it, then convert it into the equivalent integer or float. But okay, so we do the same thing, and we multiply by the chunk size or length. So we know where the chunk data begins and how long it is, and with those two things we can well, we skipped ahead here because looking at where the data begins, all we really cared about in that moment is actually the data length, whether there are any chunks of, or any sections or sectors of data in that chunk. So it would report 0 if there were no sectors of data. Again, if the chunk might exist in the table and have an offset location and all that, but not actually have like a block. It could exist but have no block section data or block data in it. Okay. Right, so then we're also looking at the modification date. This, I don't know if we're actually using this except in like error scenarios anymore. Oh, I marked it as a header, okay. But that's also useful. This basically just takes the maximum maximum value of all the last modified dates for those chunks. Again, those come from the headers of the region file, not by unpacking anything in the data itself. Okay, so at this point, it gets into the actual rendering technology, and that is essentially just finally getting to the point where we are unpacking or decompressing the chunk data. So through a roundabout way, we're getting the data portion of that, of the chunk data lifted from the file. So that's, again, the offset and length, which we talked about a moment ago. Getting it as a string again, but knowing that the chunk format, payload for each chunk, there are 5 bytes that lead that, like its own little 5-byte header that has an exact length for the compressed data and then a compression type. So we can see that the NBT compressed data length is just taking the first 4 bytes of that like local header here. We're actually not using the format, but we're still applying that same sort of padding logic there to the 5th byte compression type, and then finally taking the 6th byte and onward into a data buffer there. Again, we bail if there's no data. And then we hand that off to our zlib decompression adapter for the NBT Aternos NBT reader library. With that decompressed, we're basically left with a chunk class here that exposes all of this via a get NBT data. So this, the reader is just responsible for decompressing the data and sort of preparing it. Then the tag data or tag classes from the parser actually ends up sort of unpacking the decompressed NBT data into usable stuff at this point when we call get NBT data. Here we're applying the like caching it as soon as we've decompressed it and loaded that class information. But then everything downstream of the, we're actually looking at expand height map, so that an individual height map goes and gets the NVT data, which involves all of that, like chopping and slicing and parsing. And then this is all specific to the NVT data library. Okay. So again, this is just a PHP library that helps you read and write NVT data. Not specific to Minecraft, except that NVT is pretty much exclusively used by Minecraft. Right, so in that case, they've showing examples of a string reader, or we could be responsible for doing that z-lib decompression ourselves. This is actually a fairly thin wrapper around PHP functions that compress and decompress various formats, but there's your three formats: zlib, gzip, zlib, and then uncompressed. I assume that this string reader would just work with this, but yeah, read uncompressed NVT, gzip compressed, zlib compressed. Okay, from then on out, we are just using the library API to seek around in the NVT data. So in this case, from the root compound tag here, we're saying, okay, get a child compound tag with the key of height maps. So if we seek down through here, there's our height maps key, which is another compound tag. And then within there, get long array. So each one of these is a long array with incoming names. So in the, we're looking at this. We're getting two height maps, surface and ocean. So motion blocking and then ocean floor. And those two height maps are what determine, let's zoom in here. Well, let's go back to the root so I can actually browse around. So we're getting two height maps, and then eventually when we get to the point where we're going to render some stuff, we're comparing the motion blocking height map to the ocean floor, and if there's a difference between those, then we're coloring them blue, otherwise we're coloring them beige. So rendering specifics aside, yeah, I think that the rest of this is just all specific to outputting that data as SVGs, and doesn't really have any bearing on the map data. The height map information specifically as a long array, this is another case where expand height map, right? So we're getting a height map from the NVT data, and then this is another case where we need, where it's just a big long list of 9-bit integers, 256 values, each 9-bit integers. So if we were to, well, I'm not going to try to do any math here on the fly, but these array, 9 bits per value, but they're sliced into, 9-bit values are stored in an array of 37 longs, each containing 7 values. Really bizarre handling of this. So it actually ends up being like a 64-bit integer, but it's or 64 bits chopped into not like little groups of 9 bits, and then the last one's discarded. No idea why it's like this and not something else. There's got to be some low-level reason in the game engine that makes this easier to do calculations against, like when you're actually falling through the world or something, like physics calculations. I don't know why. This was maybe the most baffling part, and I was getting really bizarre artifacting in the world until I finally figured out how to chop this up. So the formula I ended up with there involves shifting bits, basically to carve off anything to the right of that isn't used, and then doing some bitwise modification to it to chop off the left side of it, like anything bigger than a certain amount. The -1 basically goes from something that's like a very large power of 2 to something that is 0 or more, flipping, effectively like inverting or anding the final number with some string of on bits. All right. I really haven't gotten into much more of this. I looked at the structures portion for a while because I was curious about figuring out, like, I thought I was going to have to look at all the block data, and the best way to do that would be to seek through the sections and figure out if there is which section, what the highest section has data in it, and then you could scan that through the layers and see if there's any, see where the highest block is within that section. So you'd be able to skip whole blocks of 16 by 16 by 16. Skip entire vertical sections of the world, or perhaps entire layers. Who knows? Didn't need it because we have height maps. There will still need to be at some point I'll still need to do at some point unpack individual block data to get the types of blocks that are at a given coordinate. But right now I'm pretty satisfied with the ability of this to visualize the world state and just the fact that this represents like the most math or comp sci heavy portion of the getting the data out of world files and into a space that you can interact with them. Like the rest of it is more like an aesthetic choice than anything. The functional aspects of it, I think, are basically solved. Anyway, I think I'm going to cut off there. My hope was that this provides some concrete, workable examples for managing the world data, or moving through it according to this spec, which I found to be, someone with computer science background probably understands why all of these decisions are made. To me, it felt totally foreign and involved working with data, bytes, bits at a lower level than I ever had before. So lots of learning, lots of bizarre math. Also that I, had to sort of initially take just strictly on faith, like, okay, you're telling me that's where it's going to be, all right, I'll plug that in. Oop, it's not there. What could go wrong? What did go wrong? So sorting through each of those problems. And then in some cases, once I was able to see world data in like a debugging context, figuring out why it wasn't mapping into what I thought it should look like, moving around in the game world itself, and looking at the map and saying like, well, that's weird. There isn't like a sharp incline here, or like why am I getting like weird height bizarre like spiky height maps in certain places and not others? Why am I getting world data that's repeated multiple times throughout the map? All just like fascinating questions that I'm excited to continue pursuing. Again, I hope this has some application to somebody else. If not, that's okay too, because again, it's been a blast looking into all this.